All right. How's everybody doing? Good? Good for a Wednesday? It is Wednesday, right? Okay. Good. Okay, so last time we had started our discussion on second quantization, right? And so we worked out the formalism for basically how you construct these states. So this is a system of big N, identical particles. And we've said that, when you have these large systems, especially when you have, identical particles, it becomes nearly impossible to apply, a single particle type of theory where you're compounding a bunch of, I just noticed this is a line, where you're compounding a bunch of single particle wave functions or kets. And so we decided to work in the second quantization way where we build states, kets that look like this, right, where these guys are called occupation numbers. So this is like, so this would be number of particles that have, say, some eigenvalue K1, and these are the guys that have K2 and so on and so forth. So basically you just keep track of how many particles have whatever eigenvalue that you're interested in. And the sum of these occupation numbers better sum up to be number of particles in your system. For fermions, these guys, they can only be 0 or 1, right, because of the Pauli exclusion principle. However, for bosons, they can be any number. You can pile as many bosons as you want in one of these buckets. So we started by writing down some formalism. We defined the vacuum state to be where you have all zeros in this ket. We defined a single particle state to be one where you have all zeros except for one slot where you have a 1. So this is a single particle that has eigenvalue k, or k sub I, I guess you should say. And so what we did was we said, okay, well, let's apply. We're going to use this analogy of the simple harmonic oscillator. And so we'll build up states by applying what we call a creation operator, or the ladder operator, the raising operator. Right. And so we postulated that there's some operator that we can write down that when it hits this ket, it's going to raise the ith occupation number by 1. Right? And so that gives us a way to build the single particle state from the vacuum state by applying this creation operator. And then we also postulated that the Hermitian conjugate of this operator would be like an annihilation operator or a lowering operator. So when it hits the ket, it's going to lower the occupation number of the ith element by 1. Right. And so that's good and fine. So it's basically like a multi-dimensional simple harmonic oscillator at this point. But what we have to keep in mind is that we're dealing with identical particles, so we had to build in our symmetry, our permutation symmetry, right? And so we said, okay, well, the way we can do that is to apply certain conditions on our raising and lowering operators. And the way we saw this was that by filling a vacuum with 2 particles, right? First by adding particle 1, then by adding particle j, or particle I and particle j, and then doing the reverse, all right? And because of the exchange symmetry, we know that these states for bosons will be symmetric, right? So we would expect it to be the same. However, for fermions, if we flip these particles around, which is equivalent to switching the order of these operations, should be a minus sign, right? So that's telling us that for bosons, these creation operators commute. They have a commutation relation. And for fermions, they anti-commute. So they have an anti-commutator relationship. Okay. And so you can take the Hermitian conjugate of this and show that same applies for the annihilation operators. And then for the relationships between annihilation and creation operator, you can basically go back and look at what we did for the simple harmonic oscillator and show that for bosons, it's a commutation relation. Where over here we have 1. right? And here for fermions, we have an anti-commutation relation that is just basically the analogy of this, right? But it's an anti-commutation relation. And the way you go about doing that is by defining something called the number operator, which would be AI times AI dagger. Here we have a whole bunch of particles in. So we have a bunch of, so we have to sum over all the numbers of particles that are in the ith state, right? So we would sum over all those little n's to get our number of particles. And we can, so this is an operator, right? And so the operator we can write in terms of this combination. So then we worked out how you write down operators, right? In this formalism, and we found that the single particle operator you can write in terms of just the number operator times the eigenvalue, which makes sense. So if I had particles in some system and they each had an eigenvalue of some k, right, some little k, all I need to do if I want the value of big K, the value of k for the full system, is count how many particles are in each state and multiply it by their corresponding eigenvalue, and then sum all that up. Right. And so the more general way of writing these guys turns out to be like this. So this is just in general. So that if you had an operator K in some general coordinate system, say some general eigenbasis that doesn't necessarily correspond to K. Okay. And then finally, I kind of ran through real quick the form of the two-particle interaction, which is what we're interested in because we're dealing with systems of particles and we're assuming these particles interact. And so we wrote down the interparticle interaction term, where we don't allow I equal to J. That would be like a self-interaction, which doesn't make sense. The 1/2 is to account for double counting, right? So as we sum over I, we're guaranteed that we're going to double count, so we just divide by 2. And this guy, what does it do? I forgot. It accounts for particles that are in the same state, right? So interactions between particles in the same state. And because they're identical, you basically have n choose 2 way of doing this, so that's n times n minus 1. All right. So we were able to write it down like this, introducing this delta function. Right, and then I plugged in the expressions for n in terms of a and a dagger, and put this thing in terms of what's called normal ordering, where you put all the annihilation operators to the right and all the creation operators to the left, right? And we were able to write down this two-particle interaction, right? But you can see that if I move these guys around, I'm going to get something that goes like n squared, right? Which makes sense, right? Because we have two particles, and so we should have two factors of big N, right? As we sum over these guys. Okay? Makes sense what I'm saying there? Okay. And this is the operator that you would write down in some general basis. Okay. So any questions about last time? No? Okay. So there's a lot of formalism, and today what I want to do is try to put it to use by looking at kind of a classic problem. It's called the degenerate electron gas. And I don't know why it's called degenerate. I don't remember. I probably did at one point, but it's just an electron gas to me now. But basically what it is so we have a system. So you can think of it as, how do I want to think of it? It's just a system of n electrons, right? And these guys are going to interact with each other through the Coulomb interaction. But because it's not just two particles, right? Particle 1 and particle 2, there's a third particle over here that's going to affect the interaction that these two guys have between each other, right? So it's not going to be the full-on Coulomb interaction, right? So it's going to be a screened Coulomb interaction, right? And I'll show you how we can account for that in just a minute. But it's not just a gas of electrons. It's actually, you can think of it as, the word's escaping me, but as a metal, right? So you have basically a piece of, let's say, metal. I don't know why I can't think of the word, but it's a metal, and this thing is constructed as a lattice. Okay, so if you're watching the video, this isn't going to help you, but so basically, we can think of our system as some big block. All right, let me just draw 2 dimensions, because if I draw 3 dimensions, my mind will blow up. Okay, so what we have are basically a lattice of points. Right? Everybody understand what I mean by lattice? Hopefully, okay. All right, so these points are going to be positively charged. Okay, so they're basically the nuclei, right? So we have a solid, that was the word I was trying to think of, solid. We have a solid, right? And it's made up of a lattice of positively charged particles. They're just the nuclei, right? And then what we have are the electrons. And the electrons are a lot smaller, right? But they're free to move around, okay? So this is like a conductor, right? The electrons are free to move around, okay? All right, okay. So hopefully it makes sense. Okay, so that's what we have. We have a system of n electrons, and we have a system of n of these guys, the lattice sites, right? And so what we wanted to do is construct the Hamiltonian for this system, and then next time what we'll do is solve for the eigenvalues and eigenstates. Okay, so what does our Hamiltonian look like? All right, well, let's just take the simplified version of it. Okay, it's going to be made up of 3 parts. All right, so this HEL, this HB, and this HEL-B. Okay, and so what these are, HEL is the interaction between 2 electrons. Okay, it's an interaction between 2 electrons, and what we do is, since we're interested in the dynamics of the electrons, so these lattice sites are fixed. Okay, so they don't move. No kinetic energy for these guys. We lump in the kinetic term with this HEL. This is the kinetic term for the electrons, right? And we're summing over I from I equals 1 to up to n, right? And then we have our interaction term. Okay, so this is the Coulomb interaction. It goes like 1 over r, but I'm accounting for the fact that it's a screened potential. Okay, so it's really what's called it's the Yukawa potential, basically, right? So this guy accounts for this fact that particle 1 and particle 2 don't really see the particle 1 or particle 2's full charge, right? It sees kind of a screened version of it because of all the other electrons. Okay, and so what we do is we sum over all particles I. So for the ith particle, we would have this term, right? And then we would sum over J, which would be all the other electrons, right? So this electron here, we would sum over all its interactions, all the way over to here, okay? And then we'd move on and do this particle and sum up all of its interactions and so on, okay? And you can see that we're going to double count, so we put in a factor of 1/2 to account for that, okay? And so what I have is I've written down the kinetic term and this interaction term, and we've written a screen potential. And but what we want to do in the end is take this mu to 0, okay? Because we want it to be the Coulomb interaction. But for now, let's just put this in by hand, and you'll see why in just a second why we have to put it in by hand. Okay. So that's the HEL, that's the first term in the Hamiltonian. The second term is the interaction between the lattice sites, right? So this guy has positive charge and this guy has positive charge. So they're going to interact with each other, right, through the Coulomb interaction, right, a screened Coulomb interaction. And so the way we write down this term is in terms of density functions, right? So the number density function. So this is for us, it's just a constant, right? It's just the number of sites that we have because they're fixed in position. So they don't really depend on x prime or x double prime. So it's just a number divided by the volume, right? The volume of our solid, okay? Oh, here, I have it written here. Okay, so rho, both of these rows are just constants for us for the lattice sites. It's just n over v, where v would be the dimensions of our solid cubed. Okay. So what do we have? So we can plug in n over v for both of these guys, right? And then that's a constant, so I can pull it outside of the integral, and then I can make a change of integration variables and actually do this integral. And what I find is that I get something that goes like e squared over 2. Here's n squared. This would be v squared, but one of these integrals, so this x prime integral, gives me a factor of v, right? So it's not over all space. It's over just the volume of our solid. Okay, so you see, so here I have n over v squared from the rho squared, and I make a change in variable that I can do this integral, right? And I can do this integral, which gives me this 1 over v. Or it gives me a v, and it cancels 1 over the 1 over v's, right? And so I get this 4 pi over mu squared, okay? So this is the interaction between, yeah.
Why do we have the potential screen? Is it just so we can do the integral?
Yes, it's a regularization of.
Okay. At first I thought, but then we ended up taking the lattice separately. But okay.
Yeah. So it's a regularization trick, right? So this integral would blow up, okay, right? If you consider it on its own. So I'm going to spoil. I'll give you a spoiler alert here. So we had to put this term in by hand to regularize the integral. Otherwise, like you pointed out, we're going to get infinities, right?
Okay.
But we know that can't be the case for a finite solid. So what we're doing is we're putting in this fix for right now that we interpret as a screening of the Coulomb potential. Okay.
But that interpretation isn't necessary. We can do something entirely different and still get a good result, right?
Yeah. There are other
imaginary part or something.
Yeah, there are other techniques that are more abstract, right? But this is more of a physical physically believable way of doing it, right? Is that you write down a screened potential, but in the end we want to compute this thing for the pure Coulomb potential, right? And so we want to take mu to 0, but we're going to do it at the end. Okay, so we put this term in by hand, and you can see that all of a sudden, for this one part, that if I took mu to 0, this thing's going to blow up. Okay, so this is one of the infinites. So if I look at this term, which is just a constant, right? There's no variables here; they're all constants. If I take mu to 0, like I said that I want to, in the end, this term blows up. Okay, so what we're going to have to we'll deal with this in the end. Okay, but for now, that's the reason that we put that term in there. Okay. Yeah. So this is just there's no, like I said, there's no variables in here, so it's just a constant, right? And so it's what we call background contribution. Okay. So that's the first two terms of the Hamiltonian. The third term is the interaction between the electrons and the sites. B is the I don't remember what B stands for, but B is the lattice sites, right? The background. Oh, that's what it stands for. B is for background. All right, so this will be the interaction of an electron with this number density, okay? So we have an electron and the number density interacting, and we have to sum over all the sites, right? Sum over all the electrons. Okay, and this guy is just a constant. Again, it's just n over v, so we can pull it out, right? And again, I can do this integral. It gives me some stuff, and then when I sum over this I, it gives me a factor of big N, right? So in the end, I get this HELB term as minus e squared n squared over v 4 pi over mu squared, right? And again, I see that this thing blows up. Right, so this is another term that blows up as mu goes to 0, right? And you say, well, wait a minute, this guy has a negative sign. This guy has the one we had before has a plus sign. Maybe they cancel each other out and we're okay, right? But it turns out that we're off. There's a factor of 2 here that we don't have in this other term. Okay, so we still have this kind of divergence problem. Okay, all right. So even though they have opposite signs, they differ by a factor of 2, and so they don't cancel. Okay, so in the end, when I put everything together, I've got this term, which is our divergent term that we're going to have to deal with, and then I've got the kinetic term, and then the interaction between the electrons. Okay. So as we pointed out, the first term is just an additive constant. The second term is a single particle operator, right? So what I'm doing here is we want to rewrite everything in second quantization because we're dealing with a large system of identical particles. So this is a single particle operator. We know how to write those down. And this is a two particle operator. And that's the one we worked out at the end last time. And we know how to write this guy down in terms of in the second quantization. All right, so for example, the kinetic term is a single particle operator, so we could use our generic kind of expression for an operator in second quantization, right? Where for us, our Ki, the operator inside of here is our momentum operator for one particle, and we can choose wisely, right? Because we have this choice of what basis we want to use, and so we might as well use the basis that our operator is diagonal in, so we'll use the momentum basis. All right, so the K or momentum space, right? But that's not the end of the stories. We also have to keep track of spin, right? So we have 2 degrees of freedom. We have the momentum and we have the spin, right? So we have to incorporate that into our notation. So our our states are really going to be specified by the momentum and the spin, which I call lambda. Okay, so lambda here can either be plus or minus, corresponding to up or down. Right? So that means that this operator or this matrix element that appears in my general expression for the second quantization operator looks like this. So P, when it operates on this guy, is going to give me a factor of h bar k. And then what's left over is the overlap between these two, this bra and this ket, and that gives me a delta function in k prime. So this is obviously would be really a Dirac delta function because k is continuous, but I'm just using some shorthand notation here. So this would be a Dirac delta function. This would be a Kronecker delta function. So it would be a discrete delta function for the spins. Okay. So it's telling me that this guy, this matrix element, just looks like this, right? And if I take this and square it, I'm going to get h bar squared k squared. I get the 1 over 2m that comes from the definition of the kinetic energy, and then the delta functions basically tell me that the number operator takes this form. Okay, all right. So you have to take this thing and square it, but what you find is that the delta functions all cancel each other off basically, and you're left with this. Okay, so that's the kinetic energy. The more difficult one is the two particle interaction. All right, so I would write that down using our general expression for the two particle interaction, right, which we ended with last time, and we wrote it like this, right, and this is in normal ordering. All right, so in our case, again, we've got 2 degrees of freedom for each particle. Okay, so we have let's say particle 1, particle 2, particle 3, particle 4. Okay, so these are, think of these as like initial and final states. Okay, so these are particles that are interacting. Okay, so the momentum, so these quantum states are described by their momentum and their spin. Okay, so this is like, so we have this is what's called Feynman diagram. Okay, so this is my particle 1, particle 2, particle 3, particle 4. And so you can think of time, I think the way I've written it, yeah. So the way I've written it, time is going like this. All right, so think of, you have two particles, right? They're just floating along, just having a good time. And then they interact with each other through this guy. So this is my interaction term. Okay, it's a photon, but don't worry about that. This is our interaction term. Let's just draw this big blob. Right? and then they leave, and so it's like a scattering problem, right? So they come in, they scatter off of each other, right? So they come in with momentum K3, K4, but there's some momentum transfer here from the interaction, right? So they're going to come out with momentum, say K1, K2, right? And likewise, the spin can flip, right? There can be some flips in some changes in the spin as well, okay? All right, so when we write down this operator in our general form, it looks pretty nasty, right? We've got 4 sums, right? Really 8 sums. Well, really 4 integrals and 4 sums. But let's just treat this as K being discrete for right now. And so it looks like this in a general basis, right? And now we want to choose wisely, right? We want to choose a basis that simplifies our life. And for us, it would be the position basis, right? Because here we're talking about the Coulomb interaction, and that thing is diagonal in the position basis, right? Because it's built from position operators, right? So what I want to do is choose these K's here to course our. Oh no, I'm sorry. Okay, let me take a step back. So what I want to do, I'm working in the momentum basis. But what I want to do is evaluate this guy, right, which is diagonal on the position basis. So what I want to do is insert some factors of 1 on both sides using our completeness relation for position basis, right? And those are in continuous form here. So I introduce this x prime part and this x double prime part, right? And then I evaluate V, which is depends on 2 positions, right? So when it hits one of those guys, you can pull it out. So this is just a number now. And now I've got all these overlaps between our momentum states and our position states, right? So I've got 4 terms here. But these are, if you just forget about the spin, these are just plane waves, right? So the overlap between a momentum state and a position state is just a plane wave. And we're working in this, last semester we talked about the big box approximation. So we're working in this big box approximation. So these plane waves look basically something like this. So this e to the minus ikx, but they have this normalization factor that goes like 1 over the square root of the volume, basically, right? L cubed, L to the 3/2 power. Okay, is that clear where this is coming from? Right? Okay, so I just wrote down the operator using our generic form, inserted some complete sets of states so we could evaluate this operator. Right, what's left over are 4 factors of these overlaps. And if I just forget about the spin for a minute, these things are plane waves. And the plane waves I can write like this. And like I said, we're working in this big box approximation. So if you go back and look at when we did that, you'll see that there's a normalization factor that basically goes like the square root of the volume. Okay, so now I can plug that stuff in. So that's just the matrix element that goes into, where am I? That goes into the definition of our general expression, right? But we've also got this factor here. So what I'm doing is I'm plugging in the explicit form of the potential, right? So here I have it in terms of just general, but it's the screened potential, right? So this guy. And then I've plugged in the plane waves, right? So I plugged in the plane waves, and now the spin is the thing that's left over, and I'm going to use the spinner notation to write down the spins, okay? So here, if you go back and look, I've got lambda 1, and it's going to be sandwiched on lambda 3, right? So this is like a chi, but it's a bra, so it's chi dagger, and this is going to be a chi, right? So I have chi, and it's labeled by lambda 1, it's daggered, and here's chi lambda 3, okay? So just, offline when you're at home, just work through, you can just work through this and see what I'm doing. I'm just plugging in stuff, okay? But now we want to use the fact that these guys are orthonormal, right? So I have chi1 dagger being dotted onto chi3, right? And so we know that these are orthonormal, so it's going to give me a delta function, right? And basically what it's telling me, so if you look back at chi1 and chi3, so here's chi1, or here's particle 1, particle 3. So what it's telling me is that this interaction doesn't flip the sign, flip the spin, right? That's what this delta function is telling me, right? So in this interaction, we don't have the spins flipping, they stay the same, okay? There are interactions that you can write down, potentials that you can write down where the spins do flip, right? Where you find that you have to flip the signs or change the spins, not signs, spins. Okay, so those factors of the spinors just give me two delta functions, right? And now what I want to do is try to perform these integrals, okay? And it looks daunting, but it's not that bad. What you can do is use a change of variables, right? Call y to be this x prime minus x double prime factor, right? And then just to get rid of any primes, I'm just going to call x the x double prime that's left over. Okay. So I'm doing y prime here. X prime here, I'm going to replace with y plus x double prime. Okay. And so there's going to be some x double primes left over, and I'm just going to get rid of the primes just to make it a little neater. Okay. So we have this stuff. Okay. And now here, what we want to do is, so I have y x prime, and like I said, I write it in terms of y and x. Okay. And so then I can combine everything, right? I combine everything. So I'll have everything in terms of x or y, right? So let me combine everything that's being dotted into x and everything that's being dotted into y, right? And you can see that the x term has all four factors of the momentum, where the y term just has the K1 and K3, right? And it turns out that if you look at this, it looks complicated, but it's just the integral representation of the Dirac delta function. So it's the thing that we've run into time and time again, right? So it's the integral over all space of e to the minus I some k dotted into x, right? And so that's just a delta function, right? And this delta function looks like this. And this delta function, I was going to ask, but the answer is up there. Maybe you can't read my writing. But what is this delta function telling me? Look at it. K1, it's telling me K1 plus K2 has to be equal to K3 plus K4. It's momentum conservation, right? So we can see that, just in this formalism, we've seen a couple of conservation rules pop out at us, right? We didn't impose them necessarily explicitly, but we've seen that there's a conservation of spin, right? The spin in this case stays the same, right? Doesn't flip. And we've also seen that the formalism gives us out a delta function that tells us that we have to conserve momentum. Okay. All right. So what we have are basically just a string of delta functions. So we got the spin delta functions, got the delta functions, the delta function that's telling me to conserve momentum, and then what's left is this interaction, this term here, right, where I'm integrating over y. But this is, if you go back and look when we were doing scattering theory, we've done this integral before, right? It's the integral that you do when you're computing the Born approximation for Yukawa scattering, right? And so what I'm going to do is just, kind of use those results that we had before, okay? So I'm going to do the same thing. I'm going to define this K1 minus K3 to be what we call momentum transfer, right? And then I can do the integral, and what I find is that this full term, this full matrix element, gives me this factor, e squared over v. This is the volume piece that's coming from the plane waves, right? And then part of it gets canceled off by a volume integral. But the important part is this 4 pi over q squared plus mu squared, right? And if we put it all together, we can write down the this full operator in second quantization like this. Okay, so we have these sums, the delta function that tells us to conserve momentum, so it's going to eliminate some of these sums, right? But I just keep it in there for now. This factor, and then our annihilation and creation operators in normal ordering. Okay? All right, so all that work was to basically get these two terms. Okay? This came along for the ride from our generic definition of the two-particle operator. Okay, so what we do, so now we've got the full thing. So again, here's our constant background term, right? That comes from the interaction of the lattice, right? We've got our momentum term, single particle operator, and we just computed the two-particle interaction between electrons, right? And we're treating this as a screened Coulomb potential or a Yukawa potential, right? And so this looks like, so this would be our Hamiltonian that we want to work with, right? But it still appears that, you know, like I said, we want in the end to set this kind of fake parameter mu. We want to set it to 0, right? Because we don't know what it is offhand, right? We just put it in there, like I said, to basically regularize that integral, because if we didn't, we were going to end up with infinity. So in the end, we'd like to set it to 0 just to get rid of it. But we can't do that because that first term still has this problem of blowing up. Okay, and so what we can there are tricks of getting around this, right? But what I want to show you is that this thing naturally kind of goes away. Okay, and the way you do that is to look at the last term, right? And I'm going to consider a special case where K1 and K3 and K2, and so K1 is the same as K3 and K2 is the same as K4, right? And I'm going to define those as K and P. But what does that mean that K1 equals K3 and K4 equals K2 in terms of this picture? If the momentum that this particle started out with here is the same as the momentum it ends up with, there's no interaction, right? It's telling me that they don't interact, right? There's no momentum transfer, right? So what that means is that this term here for that particular case, right? Because here we're summing over all the K's, right? So we're going to come across a case where this is true, where K1 is equal to K3 and K2 is equal to K4, right? Everybody buy that? Okay. Okay, so what we're going to end up with is one term where Q is equal to 0, and we'll have this stuff left over, okay? And what we could do, or what we can hope, is that if we perform these sums, right, we're going to pick up, because if you look at this thing, we're off by a factor of what do we need? So we need n squared over v, right? So we need a factor of n squared to come out of this thing. Right. Yeah.
Just out of curiosity, why does a constant term in the Hamiltonian matter? Wouldn't that just make it like an infinitely deep well if we just redefined our?
Yeah, you can always because in the case of like simple harmonic oscillator, like basically the formalism we're using here, you can always a constant term in the Hamiltonian you can throw out, right? You can get rid of it and just say, well, it doesn't really matter because all I'm interested in are the differences between the states, right? The differences, energy differences, right? We can't measure overall, the relative, or not the relative, but the absolute scale, right? That's the way we go. That's the way you can argue of just throwing it away, right? But it's, as a theorist, it should it should worry you that there's a term that looks like it's going to blow up in your Hamiltonian, right? Even though like you're saying, and at the end of the day, you don't really have to worry about it, right? Does it make sense what I'm saying?
Yep.
Okay, good. But what I'm trying to show you here is that that it turns out that you don't even have to do that for this case. Okay. So we have this case where we have zero momentum transfer. It looks like this, right? And what we want to hopefully show is that if I can move these guys around a little bit and perform the sums, I'm going to get a factor of n squared, right? Okay, so let's try that and see. And we pointed out earlier that the two particle interaction, it looks like it goes like n squared, right? Because it's going to have one pair of AA dagger and another pair of AA dagger once you put them next to each other, right? But you have to pass these guys through. All right. So what we want to do is put together the operators that have K, right, and the operators that have P. Well, the operators that have P are already next to each other, so I have to move this guy K over here, right? But it's not that simple because these guys are fermions, right? So that means that they anti-commute, right? So when I pass this guy through here, I pick up a minus sign. So you see I've moved it over, right, and I get this minus sign. And now I need to pass it through this guy, right? But that's not, that anti-commutator is not zero. So you get this extra term, which is basically this delta function, right? This is that one that appeared in our anti-commutation relation. So I have two terms here, right? And then if I sandwich it, if I multiply this stuff out, this delta function is going to give me this guy, right? And then I'm going to be left over. I'm going to have this term, right? So let me plug. So that was just those operators. So if I plug them back in, then I see that this first term gives me this minus sum over K and P, right? And this guy, we have the sum over the K and P and the lambdas as well. And because these both have the same spin, right? They have lambda 1, right? We've imposed that delta function that came from here. So there's no sum spin on this guy, right? So this guy gives us what we wanted, right? If I sum over these guys, this is just what? This is just the number operator, right? This is the number operator for P and lambda 2, and this is the number operator for K and lambda 1. Okay, so this gives me a factor of n squared, which I wanted, right? But what I got kind of, what came along for the ride is a factor of n, right? N by itself. And so this term exactly cancels that first term that we had, right? So if you go back and you look, we had this term, but we had this minus sign. And here, from our two particle interaction in the no scattering limit, we pick up the same factor, but with a plus sign. So it's going to exactly cancel that, okay? And the second term, let's see, the second term, where is this guy? So this is a single particle interaction, right? And it's N over V. Let's see, it's a single particle interaction. Vanishes, is small. Let me see if I can remember the reasoning. Yeah. So here you're assuming. So basically, remember the Yukawa potential. The range is determined by 1 over mu, right? And if we take the limit where L goes to infinity compared to the range of this mu, you can show that this term, which is this term here, right? Because we still have this 1 over mu squared, right? But this thing's going to vanish faster than because the volume goes like L cubed. This thing's going to vanish faster than this thing. Then this guy's going to blow up. Make sense? Okay. So what it tells us is that these guys, the no momentum transfer terms don't contribute to the energy of the system, and in fact, they help us. They cancel off those divergent terms from the background. Okay, so in the end, we can write down what's left after all the smoke clears. Right, we basically have the kinetic term, right, for the electrons, and then we have an interaction term which kind of combines all that stuff we had, right, into one operator, and it just goes like 4 pi over q squared. We can safely take mu to 0, right, and we end up with a two-particle interaction that looks like this. And you might ask, what's this prime mean? And the prime is just reminding you that, and when you do this sum, so you're summing over K, P, and Q, but the prime is telling you to not consider the case where Q equals 0, because we've already used that piece to cancel off that divergent piece. Okay. Okay, so that's the construct, how you compute the Hamiltonian for this degenerate electron gas or free electron gas. And what we'll do next time is we'll solve for the eigenvalues of the system, right, which are going to be vectors in Fock space, and we'll talk about how you can quantize the electromagnetic field in a separate discussion. Okay. All right. Any questions about that? So I strongly encourage you to go through. I mean, I painstakingly, went through all this stuff by hand. So it should be easy to follow. All right. So I encourage you guys to go through, these steps just to understand them. Okay. Because it's a cool calculation. And if you're going into condensed matter, you're going to see this. And you'll probably see some version of it in your stat mech class towards the end, I would think. Okay. All right. I'll see you Friday.